Hi, with this video we shall begin our discussion on electromagnetic waves. Specifically, we'll be discussing about the occurrence of electromagnetic waves in vacuum. We shall find out the nature of electromagnetic waves in vacuum. We shall write the wave equations for electric and magnetic fields. And finally, we shall discuss about monochromatic plane waves in vacuum in this discussion. The existence of electromagnetic waves was first predicted by Scottish physicist James Clerk Maxwell in 1864. He combined the existing knowledge of the laws of electricity and of magnetism by Coulomb, Oersted, Ampere, Faraday, and others with insights of his own to propose four elegantly constructed mathematical equations which are now known as the Maxwell's equations. He combined all the ideas on electromagnetic waves in his celebrated work Treatise on Electricity and Magnetism, which was published in 1873. So we are going to discuss about the occurrence of electromagnetic waves in vacuum. In vacuum, we assume that there are no sources of charges or current. So in vacuum, we can write the Gauss's law as del dot E equal to rho over epsilon 0, and since there are no sources of charges, we can take rho as equal to 0, and therefore this equation will be equal to 0. Now the Gauss's law for magnetism reads as such, that is del dot B equal to 0. The Faraday's law, that is del cross E, becomes, so this is equal to negative of dou B over dou T, and finally the Ampere's law becomes del cross B equal to mu 0 epsilon 0 dou E over dou T. So these are the four Maxwell's equations which are written for source-free region, that is in vacuum. So these equations form a set of coupled first-order partial differential equations of electric and magnetic fields. That is, E and B are coupled through equation number 3 and 4. Let's try to decouple it. That is, on the left hand side, and on the right hand side we'll have only one entity, that is either electric field or the magnetic field. For that, what we'll do is that we'll take the curl of equation number 3. When we do that, we have del cross E. This is equal to, by the BAC minus CAB rule, del of del dot E minus del square E, and this is again equal to, on the right hand side we'll have del cross negative of dou B over dou T. And this can be written as negative of dou over dou T of del cross B. Now substituting equation number 4 for del cross B, we have negative of dou over dou T and mu 0 epsilon 0 dou E over dou T, and Gauss's law for source-free region states that del dot E equal to 0. That is equation number 1. Therefore, we have this equation del square E equal to mu 0 epsilon 0 then dou square E over dou T square. And this is the decoupled equation for the electric field. So we have decoupled the equation, but the order of the equation is 2. So this is the price that we have to pay for decoupling the equation. On decoupling, the first order partial differential equation has become a second order equation. Now we have to find out the decoupled equation for the magnetic field. For that, let us take the curl of B. This is equal to del of del dot B minus del square B by the BAC minus CAB rule, and this is equal to del cross. On the right hand side we have mu 0 epsilon 0 dou E over dou T. This is again equal to mu 0 epsilon 0 dou over dou T of del cross E, and this from the Faraday's law is mu 0 epsilon 0 dou over dou T and then negative of dou B over dou T. The Gauss's law for magnetism states that del dot B equal to 0. That is, there exists no magnetic monopoles. Therefore, the decoupled equation for the magnetic field becomes del square B equal to mu 0 epsilon 0 then dou square B over dou T square. So we have decoupled the equation for the magnetic field and have found that it is a second order partial differential equation. So that is the price that we pay for decoupling the equation. We have separate equations for E and B, but they are of second order. So the equation that we have written for E and B bears similarity with the three-dimensional wave equation del square F equal to 1 by V square then dou square F over dou T square. When we compare the equations for E and B with the wave equation that we have already seen, we can find out that the Maxwell's equations imply that empty space supports the propagation of electromagnetic waves traveling at a speed v equal to 1 over square root of mu 0 epsilon 0, and that is equal to 1 over square root of 4 pi times 10 raised to minus 7 multiplied by 8.85 power 10 raised to minus 12. This is mu expressed in Henry per meter, and this is epsilon 0 expressed in Farad per meter. When we do the math, this will turn out to be 3 power 10 raised to 8 meter per second. That is, the electric and magnetic fields in electromagnetic waves travel at the speed of light. Now, how are electric and magnetic fields connected with each other? To understand that, we'll first learn about monochromatic plane waves. Monochromatic means there will only be a single frequency, and plane waves means those waves traveling in the z direction, but they don't have any x or y dependence. This is an approximate way of representing a monochromatic plane wave. You can just see the variation of the electric field lines. The longer the length of the line, the higher will be the amplitude of the electric field line. So this is an alternate representation for the sinusoidal oscillation. So let's drop these lines. And this is the point having maximum intensity. So we'll represent that point as having the maximum amplitude with the longest arrow, and then the amplitude decreases on its either side. The amplitude is almost 0 at this point, and then it reverses the sign. That means that we have to reverse the direction of the arrow. On either side, the amplitude decreases, and then again the amplitude becomes maximum along the upper direction, and it goes on. So this is what exactly have been represented in this schematic representation. So in this case, at this particular point, the amplitude will be minimum, and this is the wave that is being represented in this schematic diagram. So this is the point where the amplitude is maximum in the positive direction, and this is the point where the amplitude is 0, and this is the point where the amplitude is maximum towards the negative direction. And the fields are uniform over every plane perpendicular to the direction of propagation. That means that the electric field will be having the same length in every plane that is represented here. The length of the line represents the intensity of the field line at that particular plane. We can have a similar representation for the magnetic field also. So mathematically, we can write complex E, which is a function of z and t, as equal to the complex amplitude E0, then e raised to I kz minus omega t. And the magnetic field as complex B, which is again a function of z and t, equal to B0 e raised to I kz minus omega t. And omega will be equal to c multiplied by k. We shall take this as equation number 7 and this one as equation number 8. Equations 7 and 8 are solutions of the second order partial differential equation that we wrote for the electric and magnetic fields in equation 5 and 6. So far we have understood that the electromagnetic waves are transverse in nature and they can be represented by sinusoidal functions. But we don't have any clue on how these electric and magnetic fields will be arranged in an electromagnetic wave. Maxwell predicted that electromagnetic waves have a transverse nature. The electric and magnetic fields are mutually perpendicular and they are also perpendicular to the direction of propagation. Let's see how. For that, we'll take the Gauss's law, that is del dot E equal to 0. When we expand the divergence, we have x hat dou over dou x plus y hat dou over dou y plus z hat dou over dou z dot E0 x x hat plus E0 y y hat plus E0 z z hat. Then this has to be multiplied by e raised to I k z minus omega t. And this is equal to 0. So this part gives the amplitude and this part gives the phase. When we take the dot product, we have dou of E0 x over dou x plus dou over dou y of E0 y plus dou over dou z of E0 z, then e raised to I k z minus omega t. This is equal to 0. But this term will be 0 and this term will also be equal to 0. This is because in the case of monochromatic plane waves, the electric field remains constant along the x and the y direction. You can see that the magnitude of electric field varies only along the z direction. Therefore, we have E0 z, then ik e raised to I k z minus omega t. This is equal to 0, and this equation gives us E0 z as equal to 0. So that means that the electric field does not have any z component. It can have x or y component, but it doesn't have a z component. Similarly, from the equation del dot B equal to 0, we can show that B0z equal to 0. So we have understood another aspect of electromagnetic waves, that is they are transverse in nature, they don't have any z component. That is, these waves does not have a component along the direction of propagation. Now we shall try to prove yet another important point regarding electromagnetic waves, that is E and B are mutually perpendicular to each other and also they are perpendicular to the direction of propagation. For that we need to consider the Faraday's law, that is del cross E equal to negative of partial B over partial T. When we expand the left hand side and right hand side, we have x hat, y hat, z hat, then dou over dou x, dou over dou y, and then dou over dou z, and then we'll write the electric field as E0, the x component, and e raised to I kz minus omega t. If I write e raised to empty bracket, this has to be taken as e raised to I kz minus omega t. The second term is E0 y e raised to kz minus omega t, and then the third term is E0 z, then e raised to I kz minus omega t. We'll take the determinant, and this is equal to negative of partial, that is dou over dou t of B0 e raised to I k z minus omega t, and then when we differentiate, this will be I omega, then B0 e raised to I kz minus omega t. Let's expand this. So this will be dou over dou y, then E0 z component, then e raised to I kz minus omega t minus dou over dou z, then E0 y e raised to I kz minus omega t. So that is the first term, and then x hat minus dou over dou x of E0 z, then e raised to I kz minus omega t minus dou over dou z of E0 x e raised to I kz minus omega t, then y hat, then dou over dou x E0 y e raised to I kz minus omega t, then dou over dou y of E0 x e raised to I kz minus omega t. So this is z hat, and this is equal to I omega, and then B0 x x hat plus B0 y y hat plus B0 z z hat, then multiplied by e raised to I kz minus omega t. This term will be 0 because we have previously shown that the electric and magnetic fields are transverse in nature, that is, they don't have an z component. So this term is again equal to 0. And this term is 0 because it is partial of E0y over partial of x. And this term is again 0 because that is partial of E0x over partial of y. Now this term can again be taken as 0 because the z component of the magnetic field is 0. So after all these cancellations, negative of dou over dou z E0 y e raised to I kz minus omega t x hat plus dou over dou z E0 x e raised to I kz minus omega t, then y hat. This is equal to I omega B0 x x hat plus B0 y y hat multiplied by e raised to I kz minus omega t. Let's take the derivative, and this will be equal to negative of ik E0 y e raised to I kz minus omega t x hat plus ik E0 x e raised to I kz minus omega t, then y hat. This is equal to I omega B0 x x hat plus B0 y y hat multiplied by e raised to I kz minus omega t. We can cancel all the exponentials, and this will be negative of ik, then E0 y equal to I omega B0 x, and then ik E0 x equal to I omega B0 y. That is, we have equated the x and y components. In this equation, we can cancel i's on both sides to reach at the equation B0 x as equal to negative of k over omega E0 y, and then B0 y as equal to k over omega E0 x. So these two equations can be combined into a compact notation, that is B0 equal to k over omega, then z cross E0. So with this discussion, we have formulated the nature of electromagnetic waves. We have seen that the electric and magnetic fields in electromagnetic waves propagate with the velocity of light. They are transverse in nature. That means that they don't have an z component, that is a component along the propagation direction. They are mutually perpendicular to each other and also perpendicular to the direction of propagation. That is what we understood from the last equation, that is B0 equal to k over omega, then z hat cross E0. So E and B are in phase and mutually perpendicular. In phase means if this is the electric field, this will be the magnetic field, and the maxima of electric and magnetic fields occur at the same point. That is, E and B are in phase and they are mutually perpendicular. Their real amplitudes are related by B0 equal to K over omega multiplied by E0, and that is equal to 1 over C multiplied by E0. Now, how do we define the polarization of electromagnetic waves? We define the polarization of electromagnetic waves as the direction in which the electric field will be placed. So in this particular case, the electric field is along the x direction. So we'll say that the polarization of this wave is along the x direction. It is absolutely not necessary that the direction of propagation of the electromagnetic waves has to be taken always along the z direction. Let's assume that a wave is oriented along the direction shown by the blue vector or the green vector. If the direction of propagation is not the conventional z direction, then we can easily generalize the propagation of electromagnetic plane waves by introducing what is known as the propagation or the wave vector k. As you see in this figure, the wave vector will always be pointing in the direction of propagation. The magnitude of the wave vector is the wave number k. To express the propagation along the k direction, we can generalize kz as k dot r, so that the electric field will be E, which is a function of r and t. This is equal to E0 tilde e raised to I. Instead of kz, we shall write k dot r minus omega t. Then the direction is indicated by the unit vector n hat. The magnetic field will be given by B tilde RT. This is equal to B0 tilde e raised to I K dot R minus omega t, and the direction will be K cross N. This is again equal to 1 over C K cross here n hat is the polarization vector. Because E is a transverse wave, when we take the dot product of n hat and k, this will be equal to 0. When we write the real part of electric and magnetic fields in a monochromatic plane wave with propagation vector k and polarization n, the expression would be E RT equal to E0 cos k dot r minus omega t plus delta with polarization along n hat, and the magnetic field is B RT equal to 1 over C E0 cos of k dot r minus omega t plus delta, whose polarization is along the k cross n direction.